2, 1. Boom! And we're live. What's up, guys? It's your boy Andy, going all the way after some Codeforces rounds. Here we've got the last Codeforces round, which was proposed by some one of, or maybe more of, some Indian friends from Codeforces, which was pretty good. So yeah, as you can see, I'm pretty excited because I managed to solve 5 out of 6 problems, and I think that unofficially in Div 2 I'm something like place 101. And that's interesting. Is it already like judging or interesting? Alright, so I think D and E were already judged on full tests or something like that, and these are waits to be judged or something. So first of all, you know the deal. You are here, you're on Algopedia, you're on the best YouTube channel that teaches comparative programming. This is exactly why you need to like this live stream right now. You need to subscribe to the channel right now, because if you haven't joined the party, come on, look at what I have here. So yeah, make sure you subscribe, make sure you share with all your friends, and show me some love, man. Show me some love, because we are a family right now. So yeah, let's start doing this because I'm very excited. So I've seen a lot of comments from you. Some of you want B, C, D, E. Come on, I've solved all of them. Let's hope that all of them pass the full test. So yeah, I'm pretty but we'll see. So warm-up problem. I'm gonna start with B. That's unexpected, but I'm gonna start with B. We are going to stay like 2 minutes on B, just as a warm-up, because I've seen some of you guys who didn't know how to solve it. So yeah, alright, so problem B, really simple. You are given a binary string, right? So you only have digits of 0 and 1, and you need to perform as few swaps as possible, or flips as possible. One flip, you pick some 0 or 1, basically some character, and if it's a 0 you transform it to a 1, if it's a 1 you transform it to a 0. You should perform minimum number of flips such that you won't have the subsequence 0 1 0 or 1 0 1 in the final string. Cool, pretty easy, right? So maybe it is, maybe it isn't, could be tricky. So the thing is that 0 1 0 or 1 0 1, when I've seen this, I thought about, alright, so it's clear that if I have a 0, then maybe I have a couple of zeros next, then I have some 1 and a couple of 1s next, then I can't have another 0. And the same for 1, 1 1 1 1 1, 0 0 0, and then I can't have another 1. So basically all you have to do here is take into account 2 possible scenarios. The first scenario is that in the end you are going to have the string 0 0 0 0 dot 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 0, and then from some point 1 1 1 dot 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 1. That's the first scenario. The second scenario, you start with 1, right? So it's all a matter of what is the first character. If it's a 1 1 1 1 dot 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 1 0 0 0 dot 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 0. So this is all of it, right? So what you have to do, let's take the first scenario, and the second scenario you can do it alone because it's exactly the same thing. For the first scenario, basically what happens is that I'm gonna have only zeros for the first, let's say, P characters. So the first P characters are only zeros, and then the next n minus P characters are going to be 1s. Of course, you need to try out each and every P possible, right? You could have 1 0, 2 zeros, 3 zeros. You're gonna try out each and every P, right? In the range 0 n, could be 0, could be n, and for each P you basically need to know the following thing. Among the first P characters, how many 1s do we have? Because the 1s from the first P characters are going to be flipped, and then among the last n minus P characters, how many zeros will we have, right? Because these zeros need to be flipped in order to become 1. So basically you need how many 1s from a prefix plus how many zeros from a suffix. Of course, in the second scenario you're going to need how many zeros are in this first P and how many 1s are in this last n minus P. How do you do this? Yeah, partial sums. Why not? You can count partial sums, right? How many zeros or ones do I have in this prefix, in the first I characters? Or even two variables. You can iterate through the whole string once and count how many zeros, how many ones, and then you fix each and every pointer p, and while iterating with the pointer, you count how many ones and zeros are in this prefix, in the first p characters, and then of course you subtract, right? So pretty easy, right? You can code it alone, but just oh, it's accepted, so yay, one more extra, right? So yeah, basically you can see what I did here. Total 0, total 1, iterated once, counted how many zeros, how many ones, and then I start off with the minimum between this, because I take into account only zeros and only ones for the string, and then for each j, which was the p that we used in the explanation, I just count how many zeros, how many ones, and then the two possible scenarios are here, right? So b was pretty simple, just like a warm-up, right? So, alright, I need to move my camera. Oh, screen placement problem. Cool, alright. Screen not showing full. Yeah, alright. So this is a curse, right? I really have a problem with this camera. Alright, let me try it like this. Tell me if it's better right now like this. So, alright, cool. Cool, so I hope all of you got problem B, right? It's not that that hard. So yeah, now that we have solved this, please tell me in the comments if you can now see the blackboard, right? What should we do, C or D? What do you think? So tell me if this is okay. So I think the better version is to do it like this. All right, now I think it's optimal. So cool, we have done B. C or D? Let's do C or D. C or D, C or D, C or D. You know what? Let's do C. Yeah, we are going to do C. So C was pretty tricky actually, like I thought a little bit about the C, so yeah. As you know, the statement, you are given a tree, right? And you have n nodes, and this tree is unrooted, so it's just another tree, no root, cool. And you all have basically two players, right? Which are Ayush and Ashish. Alright, sorry for my Indian problem setters, but I'm not gonna use these names. I'm gonna say Alice and Bob. It's standard for math games and stuff like that. Alice and Bob, right? So yeah, Alice and Bob, cool. I'm just kidding, doesn't matter. So basically, when one of these two players is on the move, it can perform the following thing. It can select any leaf node and remove it together with the edges which are adjacent to that leaf, right? So yeah, and we are given a special node which is X, and the player who will remove the node X is going to win the game, right? So this is it. Cool, we know the problem. Let's see how to think about this. First of all, I have to mention that the problem was really tricky. I think the problem setter wanted to kind of trick us with this n less than or equal to 1000, because you think like, oh, 1000, it should be a dynamic programming or something. Nah, it's way simpler than that. So tell me if everything's okay. All right, camera is okay. Cool. Camera is okay. Thanks. So, all right. So he really tried to trick us. If you see this problem setter, you are a little bit tricky. So let me move on. Let's think about this, right? I'm thinking about this problem, and I'm like, okay, if the tree is unrooted and the special node is X, guess what I'm gonna do? I'm gonna root the tree in X. That's the first thing that I do. Alright, it's unrooted, I have a special node. That special node is the root. Simple, right? Makes sense. So, first thing I do, I root the tree in X. So I imagine X as the root. If X is the root, obviously this node is going to have sons, right? Cool. So let's imagine our 3. So, special note, x, he's now the root, right? He is going to have sons, right? Maybe 3, maybe 4, maybe 5, who knows? Well, I don't care. Because I'm a simple guy, I always think about the simplest possible scenario. So, at this point I'm like, what if x has only one son? So, x has only one son, right? Well, if x has only one son, doesn't matter what nodes do we have here, x is basically a leaf, right? So the winner is player 1. Okay, that was simple, that was too easy. Let's think about 2 sons, right? It should be harder with 2 sons. So let me Ctrl Z, Ctrl Z. Alright, cool. Let's say we have 2 sons, right? Cool, I have 2 sons. And of course, these sons have, each of them has sub 3, and nodes, and so on and so forth, and yada 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 yada. Doesn't really matter, okay? So, what's the thing here? I have got x, which is not a leaf anymore. But when would it become a leaf? X is going to become a leaf when player 1 and player 2 start removing leaves, right? We remove leaves, we remove, doesn't really matter. But at some point in this scenario, so we remove these leaves, right? And then we have these 3 nodes. And the player who is going to move next is going to lose, right? Because he doesn't have a choice, right? So the first thing that I notice is that at some point I'm going to have left the root x and only 2 sons, and in total only 3 nodes. So I have basically removed each and every other node, and I'm just left with my 2 sons. Whoever is the player that is unlucky and is left with this scenario loses. That's a fact. So when I have 2 sons, it's quite simple that if I'm player 1 or if I'm player 2, I need to put you in this position. I need to do my moves to play my cards right so that you are going to be left with these 3. So how do I do that? Well, if I want to do this and my opponent wants to do that, it's quite intuitive what's going to happen, right? When we have only 2 sons, we are basically removing leaves. Doesn't matter in what order, alright? It doesn't matter that I remove this leaf and then he removes this one and then this one and then this one. It doesn't really matter. All that matters is that no matter the order, we are going to take turns and remove these leaves until we are left with this scenario. So the thing is, the number of nodes is n, right? The number of total nodes. And the nodes x, first son of x, second son of x, these are locked, right? These are going to be the nodes that are going to be removed last, right? So I'm left with n minus 3 nodes, which basically you can imagine we have a set of n minus 3 nodes and we just remove the nodes one by one. Doesn't really matter which node from which of these subtrees, doesn't really matter. We just pick and remove nodes in turns, right? So it's just a matter of n minus 3 modulo 2, and that's it. On this example, on this scenario, when I have only 2 sons, I just need to take a look at n minus 3 modulo 2. If n minus 3 is even, right? Let's say n minus 3 modulo 2 equals 0, right? Alright, let's imagine I have 2 sons and n minus 3, let's say it is 4. 3 sons here, 1 son here. Alright, player 1, player 2. I hope you can see this because my camera I think is there, so yeah. Player 1, player 2, player 1, player 2, and player 1 is left with this scenario. Player 1 and player 2 wins. So if this is even, player 2 wins. If this is odd, right? So equals 1, player 1 wins. And this is how you solve the scenario in which you have only 2 sons. And then I'm thinking about, what's the difference between this scenario and every other scenario? No difference. Yeah, you heard me. No difference. You can have 3, 4, 5, 6 sons. There's no difference. The answer is exactly the same. The strategy is exactly the same. And let me explain why. It's really simple. You can imagine that. So, I've got a root, x. I've got 2 sons, and then I've got another 3 sons, right? Each of these sons has some sub-tree, 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 and sub-tree, right? Alright. Well, no matter how many nodes are in each of these sub-trees, one thing is for sure. In the end, I am left with this scenario: x, one node from some subtree, I don't know which one, and another node from another subtree, I don't know which one, but I don't care. I don't care. The thing is that, no matter how many sons I have, exactly 3 nodes are going to be locked, because player 1 and player 2, both of them are going to be very careful to keep 2 sons there, alive, right? At least 2 sons have to be there, right? So if you imagine that, alright, if let's suppose these 2 sons are going to be left at the end, this means that no matter what other subtrees do I have, we are going to remove until we are left with 3 nodes. So it is exactly the same thing, right? All we need to do is remove until we remain with only 3 nodes, and who is in that position, x and 2 sons, loses. So again, you take n minus 3 modulo 2, right? So this was it. It was super tricky. I really thought about dynamic programming or something like that when I've seen this kind of scenario, because I'm like, alright, n is 1000, it is dynamic programming. It's not. All that I did, it's accepted, yay, one more. All that I did is the following thing. I read n, I read k, I read the edges, and if x or y, if one of them is equal to k, I increment the degree of k, right? So I count what is the degree of k. Why do I need that? Because remember the very first case, very first scenario was when x was the node? Yeah, x. Oh, I called it k. Whatever. Was when the special node is a leaf. So this is why I count the degree. Because if the degree is less or equal than 1, so it is a leaf, player 1 wins. So I print Ayush. Otherwise, I just ask n minus 3. Is it even? Ashish. Else, Ayush. And that's it. Right? So, very tricky problem. It was way easier than probably most of us expected, right? So yeah, we have solved B and C. We are left with D and E. E hacked. My E was hacked? Oh, come on. That's nice. Come on. Tell me that my E was hacked. Was it? Not yet. Or I don't see. So, yeah. If it's gonna be hacked, that's kind of the price that you pay for being famous, you know, on YouTube, on Codeforces. You're famous, so you're gonna get a lot of hacks, but I embrace it. Let's do it. So, we are left with D and E. Which one of them should I solve next? What do you think? Which one of them should I solve next? Let's see in the comments, guys. A. Shut up. I'll have to block you, sorry. If you keep spamming the chat, I'll have to block you. So... A. Please tell the logic of A. I hate C. I've just explained C. Okay, lots of you want E. Oh, no. It's just one guy which is spamming with E. Wow. There's a lot of spam in this chat. For real. For real, guys. There's a lot of spam in this chat. But no problem. D is binary. Alright. Cool. I can't make a decision, so we'll just stick with E. Next is E, guys. Get prepared for yourself. It's not hard. Running on test 52. Alright. 67. Let's see. 71. Come on. 74. Come on. Oh, 78. Come on. Come on. Come on. Come on. Fingers crossed, guys. Show me some love. Let's see. Is it going to be accepted? If it's accepted, I'm gonna teach it. If it's not, I'm not gonna teach it, and I'm gonna teach D. How? Come on. Come on. You can do it. Come on, baby. Come on. A couple of test cases. Give me 10 more test cases. Come on. Come on. We can do this. Alright. 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 One by one. One by one. One by one. One by one. Come on. Come on, guys. Let's see. Let's get this problem accepted right now. Test 120. Come on. 22. Come on. Who's with me? 23. Come on. Come on. Come on. I have to teach this. Just give me accepted or... Alright. I'm gonna suppose that it's accepted. Is it? Alright. Accepted. Let's go. Boom. It's accepted. That means we start solving it right now. Cool. Tree shuffling. You probably know the statement. It was super cool and cute problem. I really enjoyed solving it. So, let's see. Oh, and by the way, the problems with trees are my favorites. So, whatever Codeforces round that I have, which has 2 or 3 problems with trees, I'm like, that's my round. That's my top round. I'm gonna do like the best lately because I just love trees. Give me dynamic programming, give me greedy on trees, I just love it. So, no more talk. We are given a tree with n nodes, which is rooted in node 1. And each of these nodes has one binary digit, 0 or 1, initially. And has a target digit, right? So at the end, after performing a couple of operations, we need to have in that node that target digit. And what is one operation? One operation is selecting k nodes from the subtree of any node u and shuffle the digit in these nodes as we wish. And the cost of doing this is k crossed a of u. So each node has a number a, which is the cost of picking that node's subtree. Then we pick k nodes, we shuffle that, and the cost is k crossed a. And yeah, basically that's it. Print the minimum cost to convert the tree into the final target tree, or -1 if it's impossible. Alright guys, so let me be honest with you. A lot of you know me for a long time and are on the channel for kind of a long time, and you all know 2 things about me. First is that when I solve a problem, I always think about the simpler version of it. I'm gonna do that. Second, when a problem tells me print -1 if you can't do that, the first thing that I do is think about when should I print -1. That's my thing. That's my thing. If some problem says, alright, it could be impossible to do it, I think like, when is it impossible to do it? So this is what I do. Cool. So, I'm thinking about this problem, right? I have a tree. And some nodes are going to be already okay, right? So, B equals C. The digit that is in that node is actually the desired digit. Cool. Those nodes are going to be untouched. I don't touch these nodes, I let them as they are, because they are already okay, right? So, what should be the point of picking one node which is already okay and changing its digit, right? So shuffling, swapping basically its value with another node's value. There's no point in doing that. And then I thought, there could be a point in doing that. Let me explain. If this node has value 0, and it should be 0 in the end, and this node has value 1, but should be 0, could it be possible to swap these two together? It could be, but then I'm going to need an extra node which I think should be 0. Yeah, should be 0. no, is initially 0, sorry, and should be 1. So if I do this, I'm then going to swap this node with this one, right? So I have 1 here, and I have to get rid of the 1 and store it here and exchange it for a 0. Cool. So wherever these nodes are, if the LCA, what is LCA? I think it's the least common ancestor or something like that. But LCA is the acronym for that. So these two have an LCA, these two have another LCA, and these three together have another LCA, right? So this is LCA 1, this is LCA 2, and this is LCA 3, the great LCA. All right. Well, yeah. I think it's pretty obvious why swapping these two and then swapping these two is way more expensive than swapping from the start these two, right? It is, because you pay 2 crossed the cost in L1, let's say, yeah, plus 2 cross the cost in L2 instead of 2 cross the cost in L3 or something like that. So from the start, I've already proven to myself that, alright dude, the nodes that are already okay, you're going to not touch them, right? So then I think about this. So I have these tree of n nodes, and I know what are the bad nodes, right? A bad node is a node in which B is not equal to C. So I have a couple of bad nodes. These bad nodes are basically are of 2 types, right? The first type is a bad node which is 0 and should be 1, right? And the second type is a bad node that is 1 and should be 0, right? So bad node type number 1 is when B equals 0 and C equals 1. So from 0 I should be a 1, and type number 2 is of course when B equals 1 and C equals 0, right? So because what I do is that I take nodes from the tree and I shuffle them together. All the values in the initial tree are going to be the same with all the values in the final tree. I don't change any values, I just change their nodes, right? So one thing that I really need to do is, let's say I have exactly X nodes, bad nodes of type 1, which they are 0 and should be 1. How many of these should I definitely have? Of course, X. Because if I'm 0 and I should be in the end a 1, I'm going to take a value of 1 from here, from these nodes, right? I'm going to swap myself with one of those nodes. So it should be exactly X, right? If this was X plus 1 or something like that, it's a, right? It's definitely a, how do you call it? A contradiction, right? Because the number of nodes of 1 are not going to be equal to the number of nodes of 1 from the initial tree, but they should be equal because I don't change the values, just the nodes. So, alright, this is it, right? So, if the number of bad nodes of type 1 is different than the number of bad nodes of type 2, I simply print -1 and I stop the algorithm. Now let's suppose they are equal, right? I have the tree, I count how many nodes have B equal 0 and should be 1, how many have B equal 1 and should be 0, and they are equal. What is the next observation that I'm going to perform? Really simple. Remember me? What do? I think when it's impossible, and I think about the simplest scenario ever. That's what I'm gonna do, man. So, simplest scenario ever, which is X equals 1. I have one bad node of type 1, one bad node of type 2. What do? I swap them together, obviously, right? So, let's say this is a bad node of type 1, so bad of type 1, and this is the bad node of type 2, right? In order to pick them together, I'm going to find their LCA, right? LCA. This is their LCA. And because they are 2, I'm gonna pay 2 crossed the cost of the node that I pick to be that U. But be very careful that this U could be any node, such that these two nodes are part of its subtree. So could be the LCA, could be the LCA's father, could be the LCA's grandfather, and so on and so forth, all the way to the root. Right? So here I'm actually going to pay 2 crust, not A of LCA, but the minimum between each and every node on the chain from the root to LCA. So let's call it min A, the minimum A of LCA. And as I've told you, the minimum A of some node, right, is going to be the minimum between each and every A of some X, where X is part of the chain from the root all the way to that node. Right? So again, if I pick two nodes and I find their LCA, I can pick as the node U what node that I want from the LCA to the root. This is super important because, of course, I'm going to pick the minimum one. So the first thing that I know I'm going to do is that with a DFS, I'm going to traverse the whole tree and I'm going to find this min A. It's super simple, right? If I know the min A of node, let's say if I know this min A, before calling DFS on the sun, I say that, alright, your min A is the minimum between my min A, which I'm the father, and your A, right? I know your min A, and then I can call DFS from it. So, I compute these, let's say, partial minimums, or something like that. And if I have only two nodes, it's really simple. Alright, what if I have 4 nodes? That's an interesting question. So what if X was actually equal to, right? Well, it's simple. If I have 4 nodes, let's just imagine 4 nodes. These are the nodes, right? And of course, 2 of them are going to be of type 1. Let's say type 1, and other 2 of them are going to be of type 2. So these 2 type 1, these 2 type 2. I basically have 2 possible scenarios. The first one is that I pick all of these nodes in the same group. And if I do that, I'm gonna find the LCA of all these 4 nodes. Let's say it's this node. This is the LCA. And of course, I'm going to pay 4, because I have 4 nodes, crossed min A of this LCA. Great. Another scenario is that I can pick the nodes in pairs, right? Instead of taking all of them, all 4, once, I can take in the first group 2 of them, maybe 1 with 2, or maybe this one with that one, and these 2, it's my choice. But the thing is that instead of taking all of them, I take pairs of them. Which one do you think is better? That's the question. Should I take all 4 into the same group, or should I take them in groups of 2? What do you think? Yeah, the second one. Always, 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 I'm going to pick just 2 nodes. I'm going to pick a pair of nodes, solve them. Pick a pair of nodes, swap them. Pick a pair of nodes, swap them, right? And that's, let me explain why. It's super simple. You have to think about this. Let's say this is node 1. This is node 2. And I pick them together. They are going to have some LCA, right? Let's call this LCA 1. Let's say this was the other node of the first type and this was the other one of the first type. They are going to have another LCA. Well, if I pick them in pairs, I'm gonna pay 2 crossed min A of LCA 1 plus 2 crossed min A of LCA 2, right? Instead, if I didn't do that and I've taken all 4 of them, 1, 2, 1, 2, and they have a common LCA, right? This is the great LCA. That is 4 crossed min A of the greater LCA. But you know what's the thing? This LCA is the LCA of these two, right? So if you imagine these two have this LCA, these two have this LCA, and these two have this LCA, which is exactly this one, right? So the thing is that min A of L1 and min A of L2 are less than or equal to this LCA. Make sense? Of course it does. Because let's remember what is the definition of min A, right? Min A of LCA1, which is this one, is the minimum between the value of A for each and every node from L1 to the root. And for LCA is for each and every node from LCA to the root. So in L1, I pick the minimum between more values. I have more options. The minimum could be less than what it is in LCA. So min A of LCA1 is always less than or equal to min A of the great LCA. And this is also true for LCA2 is less than or equal to min A of the great LCA. And I think this says it all. Because if these two are less than or equal to this one, of course 2 cross this one plus 2 cross this one is less than or equal than 4 cross this one, right? And this is exactly why it is always optimal to choose pairs of bad nodes, right? So again, think about min A. Think again about why this is less than or equal to the min A of the great LCA. And if you figure out this, of course, the total cost is better, is less, is optimal when I choose the pairs, not all the nodes in one group. So basically, what I noticed by now is the following thing. And by noticing this, I already got the solution. I'm going to have X bad nodes of type 1, so X of type 1, and X of type 2, and I'm going to take them into pairs. One from here, one from here, one from here, one from here. How will I do that? I'm gonna do that as soon as possible. Right? Let me explain. By as soon as possible, I say that I try always to take the pair of nodes which have the LCA as close to them as possible, right? So if this is a node 1 and this is a node 2 and this LCA are here, of course I'm not gonna pair this one with another node 2 if their LCA is here, right? Of course I'm gonna pair these two because this is the LCA, not these two because the LCA is way farther than this one, right? So again, when a node is closer to another one, let me put this in other words. All right. When the LCA is closer to those nodes, it is better, right? Because we have seen that this min A is less than or equal than this one. So I really want that I pick this pair of nodes such that the LCAs are as deep as possible, right? And this is where I knew that I'm gonna go for a greedy approach. I'm gonna do a greedy approach in which you can basically imagine that you start from the leaves, right? So you basically start from the leaves, and each time you are in some node, you think about this. All right, this is node, right? If this is node, these are its sons. In each of these subtrees, I'm going to have some bad nodes, right? So here I have some bad nodes of type 1 and some bad nodes of type 2. Bad nodes of type 1, bad nodes of type 2, and so on and so forth. The idea is that let's take this subtree for example. If in this subtree, let's say, not this one, alright? It's way more nodes than that. Let's say I have 3 bad nodes of type 1 and 6 bad nodes of type 2 in this subtree, right? If I do that, this means that I'm gonna take these 3 of bad 1 and pair them with other 3 of bad 2 from this subtree, right? So I take 3 from here, 3 from here, and 3 from here, and I pair them together. And I'm left with 3 bad nodes of type 2, which I'm going to propagate to the root, to the node, and I'm going to solve then, right? So this is how I want you to imagine this greedy approach. I want you to imagine that we want to solve the nodes as quick as possible. We start from the leaves and we move up and want to pair these nodes as quick as possible, right? So if I have 2 nodes, 1 and 2, if I can pair them now, I'm gonna do it, right? So when I'm in node, right? When I'm in node and I try out this sun, I found how many bad of type 1 and bad of type 2 nodes I have. I pair as many as them that I can. In this case 3. I have 3 pairs here, which is basically going to be, so 3 pairs, what does it mean? 3 crossed 2 crossed min A of that sun, and so on and so forth, right? So yeah, probably in order to explain this better I should take away more complicated example and show you on paper, but we don't really have time for that. It will take at least half an hour more, something like that. But this is how I want you to imagine, right? Take your pen and paper and take some example and think about starting from the leaves and moving up, and when you find 2 nodes of type 1 and type 2, you try to pair them together, and you are going to pair them together in the LCA, right? And this is what you should think about this. So accepted, guys. Please don't spam the chat. Yeah, please don't spam the chat. So yeah, let's see the source code and you'll probably have a better idea about this, right? So what I do is that I read n, the number of nodes, I read a, b, and c, the cost from the node, the initial digit and the final digit, and then I read each and every edge, x and y, and I compute the min a, right, which is the minimum from this node on the chain to the root, which min a of 1, which is the root, is initially a of 1, and I start the DFS, right? With the DFS, I'm going to go with this greedy approach and pair the nodes together. So at this step, I am at node and I remember the father, right? Because I don't want to visit the father again. That's classic. So, and I initialize an array of bad nodes of only 2 values, 0 and 0. Bad nodes of 0 means how many bad nodes I have that are initially 0 and needs to be converted to 1, and how many of them I have that are initially 1 and need to be converted to 0, right? So this is the type 1 and type 2 nodes. Then I try to see if this node is bad. So if b of node is not equal to c of node, that means this is a bad node, right? Node. So bad nodes of b of node plus plus, right? I increment the size of that category. And then I try out each and every son. If it's equal to the father, just continue, because I don't want to visit the father again. If not, I compute the min a of this son, which, as I told you, is the minimum between min a of node and the a of the son, right? Pretty basic. Then I call DFS of son with the father node. And what this DFS returns is a pair in which the first argument is basically, as you have seen, when I go with DFS on a subtree, I will remain only with nodes of one type, right? So basically, if let's say I had 3 nodes of type 1 and 7 of type 2, I construct 3 pairs and I remain with 4 nodes of type 2, right? So after pairing all the nodes that I can in some subtree, I'm gonna remain with some nodes of only one type. So I remember in the first value what is the type, either 0 or 1, and how many nodes of that type I have left in that subtree that I couldn't pair with any other nodes, right? And I just bad nodes of remaining dot first plus equals remaining dot second, right? I increase the number of bad nodes from that subtree. And then what I do is that I pick the minimum between bad nodes of 0 and bad nodes of 1, and this is the number of pairs that I can construct. And I increase the answer with 2 crossed x crossed min a of node. So basically I'm in node, right? This is the current node. I have the subtrees, and from this subtree, no, from all of these subtrees, I remain with some type 1 and some type 2. I construct x pairs, and for each pair I pay 2 crossed min a of node, because this is the node where I paired those nodes, right? This is that LCA of the nodes, right? And then of course I decrease bad nodes of 0 and 1 by x. If they are both 0, I return 0, 0. Job done with this subtree. I don't have any reminder. Then if bad nodes of 0 is greater than 0, if father is 0, answer is -1. Otherwise return 0 and bad nodes of 0. Else, if father is 0, answer is -1, return 1 and bad nodes of 1. Right? So what I do here is that I find out what is the type of the remaining nodes, and if it is 0, I return 0 and how many of them are there. If it is 1, I return 1 and how many of them are there. If I have remaining nodes which weren't paired with anybody, and I am in the root, which means father equals 0, this means I should return -1. So that's it, guys. Again, take an example. If it is unclear, trust me, on this kind of problems which are trees and greedy on trees, you need to use your pen and paper and imagine what happens. Once you do that, I'm sure it's gonna be clear. But this is basically the main approach. So you notice that type 1 and type 2 have to be of the same size, let's call it x. Then you prove, as I did, that it's always optimal to choose pairs of nodes and don't take more than 2 nodes in the same group. And you have the proof with the LCAs, and after you notice that, you greedily pair the nodes, as I've told you. From the leaves, you try to pair them as soon as possible, because the sooner you pair 2 nodes, the minimum A in that LCA is going to be smaller, so the smaller the total cost, so the optimal the solution, right? That's it. Cool. Alright. This was it. Yeah, the root can be bad. Sure. The root can be bad. Why not? The root could be bad. Yeah. So, awesome. It seems like all of it passed, which is pretty cool. How do I find my... Alright, place 100. That's pretty cool. Nice. So, I think the rating is going to have some boom, which is good because we need to get to that yellow, right? That's the main target, the first target. Get to that yellow. Right. I don't know if you have much time for problem D. Some of you want problem A. Alright, let's do A first. Let's do a little bit of A. Alright, A. Be very careful because we are not going to waste a lot of time with A. Alright, you are given an array. And you should choose exactly X elements such that their sum is odd. That's it, right? So, I have n elements. I have to pick exactly X such that their sum is odd. Cool. What I think about? Well, how many odd values I have in this array and how many even values I have in this array. Right? That makes sense. Then, in order to have an odd sum in this subarray that I pick, or I don't know if it's subsequence, whatever. If in this subsequence I want to have an odd sum, what does it mean? First of all, the even elements are going to make the sum even, but the odd elements are those that matter. I need to have an odd number of odd elements among these X elements. This is the main thing, right? So take as many even elements as you want, doesn't matter, but take an odd number of odd elements, and in total take exactly X elements. So on problem A, to be honest, I had problems too. Look at this. First submission is a wrong answer. Yeah, so you weren't the only ones which have problem on this A. I had a little bit of problem too, but nothing that we couldn't manage, right? So let's actually take a look at this wrong answer source. And what do, right? I read n and x. I read each and every integer. If it's odd, I increment the number of odd integers. If it's even, else I increment the number of even integers. So I know how many odd, how many even are there. First of all, if there aren't any odd elements, I print no. Because I only have even elements, so if I pick x even elements, the sum is even. See how? No. Else, I take a look at this odd number of elements. If the number of odd elements is even, I'm gonna decrement it. Because let's say I have 6 odd elements. If I have 6 odd elements, I'm not gonna use 6. I'm gonna use at most 5, because it has to be odd, right? So what I do here is that if it's even, I decrement it, and then I pick the minimum between x and that number after I made it odd, basically, right? So let's imagine I have 6 odd elements. It's even, I decrement, now there are 5, so I can use 5 odd elements, but I can use at most x, so I take the minimum between x and the number of odd elements, and x minus this minimum is the number of elements that are going to remain, so I'm going to need this many even elements, and then I check. If the number of even elements that I need is less or equal than the number of even elements that I have, I print yes, otherwise print no, right? So count how many odd, how many even, make sure these odd elements are odd in number, take the minimum between these two, and just check if you have enough even elements. What I got wrong here is one scenario in which x was less than the number of odd elements, right? So what do here is that first of all, I take the minimum between these two, number of odd and x. So I limit that number of odd to be x, just to be sure. Alright, you're not gonna use more than x elements, so you're gonna be at most x. Then, if after I have limit you, you are still even, I'm gonna decrement you, and after I do this, I compute how many even elements I need, right, to have x in total, and I check that, and that's it, right? So I hope everything's clear. I hope everything is clear. Lol, he confessed. Yeah, I did. I had problems on A. That's like a real confession, yeah. So yeah. Alright, so that was the thing, right? Count how many even, how many odd, limit the odd to x, then if they are even in number, decrement them, and then you can check if everything's fine. And problem D, guess the maximums. I'm going to do a quick explanation about this because we don't have much time left. But some of you in the chat said that it is binary search, and it is super amazing. The problem is really, I really enjoyed solving it. The thing is that you basically have an array of n elements, but you don't know the values in that array. You just know those subsets that are disjoint that he picked for the password. He picks a subset, let's say subset number 1, and the first character of the password is the maximum between all the elements that are not in that subset, right? So immediately I think about this. When I have to pick the maximum between some subset of elements, I think about the maximum in the whole array. So I suppose, alright, I'm gonna have an array of n integers. In this array, I'm gonna have a maximum element. Let's call it max. This max element is going to be on some positions, right? Maybe I have 4 elements that are equal to max. I don't know where, but let's suppose I have them. First thing that clicked to me is that these subsets that he chose and we are given in the input are disjoint, right? So I'm thinking like, if they are disjoint, and come on, all right, let's erase this pretty quick. If these subarrays are disjoint, right, and this is the array which has n elements, and let's say I have a value of max here, another value of max here, and another value of max here, 3 maxes, right? If there is one subset, which, let's say this subset, which basically contains 2 values of max. So if let's say subset number 1 for example, has these indices, this means that there's no other subset, S2, S3, dot dot dot, Sk. None of them is going to contain any more these values of max. So if none of these subsets contain these two values of max that are contained by S1, this means that the password for them, P2, P3, Pk, is max. Because if they don't contain max, this means that the maximum between every other element is max, right? And that was the idea. That was the whole thing. Basically, because they are disjoint, if there is, maybe not S1, that's the problem. I don't know if it's S1, S2, S3 or some SP. But, oh, I now realize that I have my camera here and you probably don't see. Alright, cool. So, maybe not S1, but if among these subsets, S1, S2, SP, Sk, if among all the subsets that we are given, there is one of them, SP, right, which contains one of these maxes from the array, right? So if there is this SP and the max is part of SP, right? Let's call it max k because there are actually more k's. One of the maxes, right? If one of the maxes is part of this SP, this means that this max is not part of the other ones, right? So this max k, let's call it, which is part of SP, is not going to be part of S1, S2, dot dot dot, SP minus 1, SP plus 1, dot dot dot, Sk, right? So all I need to find out is whether there exists some subset among these k subsets which contain at least one value of max, which is the maximum between all the array. If I find one SP like that, I know for sure that all the values in the password are max, except the value of this SP, which could not be max, right? So basically what I do is that I have to find this SP. If I find this SP, it's cool, the password is max, so max, max, dot dot dot. On position P, it's not necessary max, I have to find it, and then max, max, dot dot dot, only maxes, right? And of course, if I find P, I'm just gonna do a usual query, right? I take the SP, I take the other indices which are not part of SP, I do that query, I know that value, right? So this is really easy to find. What is hard about this problem is find this SP. I have to find one SP which contains a value of max, or find whether there is no SP maybe which contains a value of max. If there is no subset which contains a max, the password is only max, 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 max. If there is one, maybe that element is not max. And how do I find, right? How do I find this SP which has the value of max? I'm gonna binary search it. How did I come up with that? You can perform 12 queries, right? So the problem says you are not allowed to perform more than 12 queries. And the length of the array, the length of k, the number of subsets, is 1000. So I have 1000 subsets. I need to find a special subset with only 12 queries. Duh, it's binary search, right? And I'm gonna tell you quick how we do the binary search, and then you should be able to solve it by your own. Basically, you take all the subsets, SP, SP plus 1, blah blah blah, Sk, and of course this is the left initially, this is the right. You take the middle one, right? And what you have to do is ask yourself this: is there between all these subsets one subset which contains the maximum? Well, if there is one subset here which contains a maximum value, this means that if I take these subsets and I unite them and I create a new bigger subset, if I query on this, so query on this greater subset, this query has to give me maximum. And that's how you do it. That's it. Left is initially 1, right is initially k, you take the middle, and then each time you want to validate the middle, you take these subsets, you unite them together, so you will have a greater subset of indices, and you query on that subset of indices. If the maximum between all those indices is max, that means that the value max is somewhere. If it is somewhere, that means that it is in some subset from this first P. So what you do basically is that you suppose the answer is here and move and search in this range. If these united don't have any maximum, this means that you have to look for greater ones. And that's it, right? So yeah, 12 queries, log of k, binary search, take the prefix, unite them. You can do this brute force with a for loop. That's pretty simple. Query that greater subset, and if the answer is max, then the answer, the SP, is going to be there. So you are going to limit the search of the binary search to that prefix. And you start looking there and do this over and over again, right? That's it. That is it. Yeah, best YouTube channel. Thank you, boss. You are all welcome, guys. Thank you for being here. And yeah, let's make it awesome. Cool. So, alright guys, I'm really excited. I can't wait to see how my rating will change about this. First of all, thanks for being here. Thanks for competing to the round. And yeah, I really enjoy solving these problems with you. I really enjoy doing these lives. And if you enjoy them too, please show me some love, man. Because as you noticed and asked me, I have a lot of other things going on. I have a job, which I'm gonna tell you about it. I'm a student and I have a lot of projects, which I'm gonna tell you about it. And I'm working on a super amazing project that is going to change the whole competitive programming and coding interviews and basically informatics teaching forever. Like, what I'm gonna do is really going to change the world. And how do you see me right now explaining these problems? That project, man, when it's ready, and I'm very excited and it's gonna be ready, it's going to be the boom. I'm super excited to share it with you, but we need patience, we need support, so show me your love. Please like, love these live streams, subscribe to the channel if you haven't, join the party, and yeah, stay tuned, share with the friends, and show me the support, man. I really need your support, and I really need to see that we are a family, we grow together, and we enjoy up-solving, not only solving, but up-solving the problems from the rounds. Again, this was Andy. A lot of love, like, subscribe, hit all the buttons, and see you on the next contest, guys. Have a good one. 3, 2, 1, and we're live. We are off.